The talk today is about some set of cryptographic techniques to provide more functionality and security to blockchains. These based on several works. I listed here the union of authors, and at the last slide, which I think you will have access to, has a list of papers that are relevant to this subject. And actually the next talk by Tal is also part of this big project. So I don't think I have to tell this audience what a blockchain is. In general, it's a complex creature, but let me say that the part of this creature that is significant for this talk, or the way I will look at the blockchain, is as a computing platform with a broadcast channel for communication. Actually, the actual blockchain is a distributed network of many nodes. We can think about thousands or eventually maybe millions, which is all the time doing some computations. The basic thing is financial transactions, but things can be more complex as smart contracts, where there is more general computation, and all of these things are being decided and put in the blockchain through some consensus protocol. Now, the way we would like to think about this, in particular in cryptography, is as this blockchain, a well-functioning blockchain, as when we look at it as a computing platform, as a trusted party. Okay, anything that it outputs, we can trust. Computations were correctly, the information was recorded correctly, etc. So, can we really think about blockchains as trusted parties? So, on one hand, yes, all the integrity and immutability properties are things that we do expect blockchains to deliver, and including correct computation, but that is when you are using inputs or data that is public. It's on the blockchain, it's broadcast. Now, if we want to actually compute with secrets, then blockchains are, at least plain blockchains, are much more limited. In particular, for example, smart contracts that cannot carry secrets in themselves, because everything is open. So we want to talk about how we can actually make blockchains to be able to carry and process secret information while keeping it secret, or we're keeping it secret as much as an application needs. So we have this bunch of nodes that, miners, validators, whatever it's called, and we assume an attacker that can attack a subset of parties, up to some ratio of the parties can be attacked, and we consider the strongest form of attack, which is malicious attack. When a node becomes corrupted, it can act in any deviate from the protocol in any way. And we also think about the attacker as being a mobile attacker, which means it can at some point attack some nodes, at a later point some other nodes. In total, it can actually eventually have corruptions of everyone, but at any given time, it should not be more than a assumed fraction of the nodes. Wait 1 second. Doing the wrong. Okay. Wait. I'm pressing the wrong. Yeah. So this malicious and mobile attacker. Now, one thing that we want is to have secure computation, but also scalable computation. Scalable means that when the blockchain grows, the complexity of the computation doesn't grow with the size of the blockchain, right? We all say that I work for Algorand, so Algorand is very scalable, and everyone is very scalable. And really the point is that right now most of these blockchains are not large scale, but the idea is that when we go from thousands to millions of nodes, the computation stays as it is now. And in order to and one of the things that we want to optimize is broadcast bandwidth. That's one of the costs. So one approach to do this scalability, which actually Algorand already is doing, that is that instead of asking everyone to do work all the time, every period of time you choose a subset of nodes, and that subset does the whole, applies the work during that period of time. And if that subset, you can choose it with a size that is independent of the total number of nodes, then you achieve the scalability that we are interested. And the way Algorand chooses the committees of these performers, and we will adopt here, is that we choose just at random, and by choosing them at random, if there is enough of an honest majority in the total blockchain, then by probability theory, the subset that you take will represent, you have to be careful about doing the numbers here, but the idea is that, again, doesn't matter if there are millions nodes or if there are 10,000 nodes, the probability theory works in both cases. And the point is that we want to choose them in a way that guarantees with very high probability that there is a majority of honest parties, or in the case of a proof of stake, of honest stake in the committee. Now, one technical challenge here is that, let's assume that we have in the total, the total number of corruptions is 25% of the whole network. Now, we choose a very small set of performers, let's say 2% of them. So the problem is that the adversary that can corrupt adaptively, and 25%, of course, it can go and corrupt the 2%, right? It has corruption budget to do that. But that is the case if, okay, so here, it ate, the 25% ate the 2%. But this is possible only if the attacker knows who it needs to, knows who it needs to attack. Okay, so if the committee is public, then we cannot avoid, at least at the level of the model, that all these this committee will be corrupted. So the question is, and this is what we are going to do. We are going to choose committees that are unknown beforehand, and the challenge here is that how do we choose the committee that remains secret while they can do their job, with part of the committee members being adversarial, and the only thing that they have to talk to each other is a broadcast channel. There is no point-to-point secret channels or anything like that. So this brings us to the model that I'm telling you here, which we call it a YOSO model or YOSO protocols, where YOSO means stands for you only speak once. So the idea is that for the attackers, see all the nodes are the same; they are interchangeable in the adversary's view until they send messages. So if a committee was chosen, and we will choose it in a way that the adversary does not know, no one will know except for the committee itself. The attacker will know that I was in the committee only at the moment in which I send a message. So I'm a node. I can monitor the broadcast. There is some messages that may be broadcast that are for me, and only I will know, or something like that. Yeah. So committee members will know that they were chosen, but the attacker will only know that they were participants when they send a message. So the idea is that when I'm chosen to a committee, I will do some work. I will know that I'm selected. I will do some work. At the end of the work that I do, I erase all my state and output the message that I need to output, and that's it. At this point, if the attacker wants to corrupt me, it can do that, but it's too late, all right? Because I did my work and I erased any secrets that shouldn't be there. So it's too late for the attacker to learn anything from attacking that node. So, we see this as a new formal notion, but of course, there are examples. We know examples in the blockchain world of YOSO protocols. For example, Bitcoin is a YOSO protocol because when, you don't know who is going to propose the next block, and once the block is submitted, if the attacker goes to that participants and want to change the block, it's too late. So we have this Nakamoto consensus with this property, and we have more general these lottery mechanisms or cryptographic sortition where no one can predict the winners, but winners can prove that they were the ones that were chosen. And you can choose full committees this way. Again, Algorand is doing that as part of the consensus. Here we are expanding the functionality with more, not only more complex operations, but also with secrecy involved. Okay, so when the operations that are going to be performed are public, they don't have any secret input, then things are relatively easy. I can self-select, okay, like in the case of sortition, and apply my role to the information, to the public information. However, if there is secret involved, if I need to receive some secret to do my operation, then I have an issue because I cannot self-select. If I am the only one that knows that if I select myself and I am the only one that knows that I'm selected, then there is a question: how do I get the secret inputs? Okay, with the public inputs, that was not an issue. It was a broadcast. It was part of the blockchain. So we will need to to change the ways in which we select committees. On the other hand, if I have if I can work on inputs that are secret, then this opens a big space of operations that we cannot do now. For example, one of the things that we want to support, there is no smart contracts in Bitcoin. Now, if in Algorand you can work with secret information, it means that a smart contract on Algorand can actually produce a Bitcoin transaction, okay? Because now we will have available a secret, which is the signature for a Bitcoin account that now a smart contract on Algorand can actually apply. Or you can have smart contracts for Ethereum working on Algorand. For Ethereum does have the smart contracts, but it's cheaper and more efficient to do it on Algorand. So that's one example. You can have a smart contract that carries some encrypted medical information, and the smart contract is actually a policy that tells you when you can decrypt and for whom you can decrypt. The challenges here are first of all, you need to have specifications of protocols that have abstract roles. For people that are used to multi-party computation, when we specify a protocol, you have parties, party A sends a message to party B, etc. Here, we will have abstract roles that will exist at the protocol level, but then they will be actually mapped to actual machines, actual nodes during execution, okay? So we need a protocol specified that way, and then we need an assignment of roles to nodes that happen in real time, and we will use, I mean, one question is how do you send, if I am now performing a role and I need to send some information to someone to do a role in the future, how do I pass that information when we don't have, point-to-point channels? So you can think about, if you know about identity-based encryption, now you can think about role-based encryption. You encrypt to that role 7 in round 18 or something like that. So I definitely not explaining how to do that, but these are the kind of things that we need to resolve. And we show that actually under this protocol, you can actually do secure multi-computation. Actually, you can do information security, MPC. And this is not a protocol that I expect people to use it. It's not, but it's more of a feasibility result, but it's interesting that it can be done. And you can do things like threshold cryptography, signatures, encryption, etc. And this gives a lot of power to do blockchain applications such as Oracle state proofs, smart contracts with a secret in them, and stuff like that. Tal will give a presentation on a follow-up work, which is more concrete and more practical. So thank you. Yeah, and there is a list of papers at the end. If,
I guess I put my microphone stands up here.
Yeah. Can you go back to the previous slide? I had some questions. So this information theoretic user and the computational user, the MPC, can you tolerate let's say for the computational, can you tolerate a corrupt majority? Or
no,
you need
no. We can tolerate up to 29%.
What about the information theoretical one?
Well, okay. So the information theoretic, the restriction on 29% is because of the assignment protocol. Mm-hmm. See, the assignment protocol that needs to choose, at random a committee, all right? We need that committee to have a majority, 51%. When you take, when you want 51%, you need to start with more of honest parties. That's where the thing. The protocol itself, if you say, someone gives me the assignment from the sky, then also it can be done with 50%, the information theoretic one.
I see. Yeah, I guess maybe this is more of a comment. I'm just I'm very interested in the Yoso model. And I guess I had a paper in Crypto 2019, which had, I think, a similar motivation, but the model is different. We were also considering a setting where there's potentially high churn. Let's say in every round, the set of honest parties may be different, but we guarantee there always exists a majority who are honest in every round. And there I think we also explore very similar questions, like whether we can do MPC. And then we also, for instance, gave constructions for both Byzantine agreement and MPC in that model. So I think it's very interesting to compare these models and see whether...
I mean, I didn't do any literature comparison here, but there are several papers with this flavor, I mean, again, Yoso is a good model to define, and the best thing about Yoso is the name, Yoso. But as I said, Nakamoto consensus is a Yoso protocol, so in that sense, it's not new. But anyway, when you look at it on this side of secrecy and stuff, actually gives you a good power. And now that I'm done with Yoso, Tal will tell you why you shouldn't use Yoso. No, so relax. I mean, when you want to be really, really practical, you need to start doing some relaxations, and that's it.
I see. So I guess if I want to ask about open questions, maybe I'll ask you too, and then I will then ask Tal. Like, what do you think are the exciting open questions?
So improving on role assignment. I mean, assignment to actual machines. That's something that will be very interesting. The other thing is that I'm running TALS, but this is here I'm talking strictly about you only speak once. We take seriously the once, but the idea is that the attacker will not catch you before you talk. But maybe you can actually talk twice, but not for too long time, and that significantly helps in performance. So understanding all these parameters is significant.
So just a follow-up question. So when you said that it would be interesting to explore the improvement to the role assignment, what exactly do you mean? Do you mean to improve the adversarial threshold, or do you mean to improve some kind of efficiency, or?
I mean, performance. Performance instead of computation, in the sense of communication, of course. Improving you still will need more majority than 50%, at least if the way you choose is you choose at random. Of course, that's another relaxation that you can have. I mean, this is the way we look at this problem, but you can also think about situations where committees are more static. So there is many parameters to play with.
Can you expand more on what a role is in this context?
So, if you're familiar with multi-party computation or in general protocols, not only in cryptography, then you have Alice and Bob, Alice saying something, Bob saying something, then Charlie something else, and you define a protocol like that. And when you think about that, it's abstract parties, but you think about these things really that when you're going to run it, then there will be a machine called Alice, a machine called Bob, a machine called Charlie, etc., and they will talk to each other. Here, abstractly is the same. I mean, you have these abstract parties, but they will not be assigned to static machines, as we think, but to something that changes. And roles will be, party. Usually, most of it. I mean, all of the things work on committees. Okay, so a role will be something like player number 5 in the committee of round 17. Okay, things like that, and then you will need to actually say who is player. I mean, the actual machine, actually node in a validator that will play the role of 5 in round 17.
Yeah. Okay. Cool. Makes a lot more sense.
Okay, thank you so much, Hugo.
Okay, thank you.
Thank you.